Hello everyone. Today we will see the addition reaction, which is model 2 in basic reactions in organic chemistry. So what is addition reaction? So addition reaction is the addition of a small molecule, that is addition of two atoms or two groups across the double bond or a triple bond, or you can say an unsaturated compound, right? So a typical addition reaction example is hydration, right, or addition of water over the double bond, or we can say catalytic hydrogenation, that is addition of a hydrogen molecule on the double bond. So you can see here as an example. For example, you can add a water molecule, that is H and OH on the double bond, and for the hydrogenation reaction, that we call it as a reduction reaction, reduction of the double bond. So you can see the each hydrogen atom added on the each carbon of the double bond, right? So this is a simple example of a addition reaction, right? So if the addition reaction has to occur, means we need a starting material, that is a double bond unsaturated compound. It can be either double bond or it can be a triple bond. Okay. So generally the organic compounds has a sigma bond and unsaturated compound has a pi bond, right? So if we take a simple alkene, we have one sigma bond, that is mentioned here as a straight line, and the pi bond, that is mentioned here as a arrow, curved line, right? So we are going to add a halogen molecule, that can be either iodine, bromine or chlorine on the double bond. So that halogen molecules added on the double bond, okay, which produces the addition product. And similarly, if we do the addition product on the alkyne means a C triple bond C, right? So first it will occur as a stepwise manner. So the first addition of the halogen molecule added on the both the carbon atom of the triple bond, and the second molecule of the halogen will be added further to the second pi bond of the intermediate product, right? So totally we will have 4 halogen atom added on the triple bond. So the addition reaction has nearly 4 types. One is electrophilic additions, free radical additions, concerted additions, and nucleophilic additions. So these are the 4 types of addition reactions. Okay. So first we see electrophilic addition reaction. So the electrophilic addition reaction. So whatever the reaction we have seen as a halogen addition on the double bond, that is a kind of a electrophilic addition reaction. So this occurs majorly, right, and this is the simplest addition reaction also. Okay. So this occurs through the mechanism, as you can see here. When the bromine molecules come closer to the double bond, the bromine molecule slightly polarizes, that means partial positive charge on one bromine and partial negative charge on another bromine, right? Because of the pi electron. The pi electron generally we consider as a electron rich center. So when the electron rich center approaches the bromine atom, it polarizes the bromine molecule, and then partial charges generated on the bromine, right? So once the partial charge generated, the electron rich center of the pi bond, it attacks the positive partial positive charge on the bromine atom. So as you see here, once it attacks, the complete pi bond will be, bond pair of electron will be given to a bromine atom in order to make a CH2Br bond, okay, sigma bond. So once that sigma bond made between the CH2 and Br, there will be a positive charge on the carbon atom, right? That is called a carbocation. And when there is a bond formation between the carbon and the bromine, obviously there will be a bond breakage between bromine molecules. Okay. So this bond breaks, and then the bond pair of electron of the bromine molecule will be taken on one bromine, so that bromide ion will generate. Okay. So now these Br minus and carbocation both will combine each other as a electrostatic interaction. So then finally the addition product comes. So each bromine will be added on the each carbon of the alkene, right? So this is how the addition reaction occurs. Similarly, if you have a different kind of nucleophilic nucleophilic reagents in the reaction mixture. For example, after the first addition of the bromine, if you add an external nucleophile, for example chlorine minus or nitrate ion, right? So that nucleophile, that is the negative charge species, will attack on the positive charge, that is the carbocation, and it produces the um, um, Br and then chlorinated product and bromine and nitrate product, right? So this is how we can generate the unsymmetrical compounds. And this bromine addition on the alkene is one of the characteristic test for the identification of the unsaturation. For example, in the +2 or in the BSc chemistry practical, we do to identify the unsaturation, we add a bromine water on the compound. If the color is disappeared, we say it is an unsaturated compound. If the color is not disappeared, then that means it is not a unsaturated compound, right? So the disappearance of the color, the color in the sense, generally the bromine will be like a orange, very dark orange color, in orange in color. So the disappearance of the color indicates that the bromine added on the double bond. So once the bromine is added on the double bond, that means once it reacted, then that will become a colorless, right? So that is the characteristic test for unsaturation. So the electrophilic addition happens across the double bond. So each bromine will go on the each carbon atom, right? So far we have seen just a general mechanism how it occurs, right? But all the addition reaction always gives a trans product. How it happens? If we do a general addition reaction, how all the addition reactions can give a trans product? So there is a mechanism, the mechanism behind that, right? So when the first bromine molecule which adds on the double bond of the alkene, it makes a bromonium ion as a three-membered cyclic ring, as you are seeing here, right? Bromonium means Br plus bromonium ion it forms, right? So the first step always occurs like same. So you see here the alkene attracts the bromine and it partializes the bromine ion, and one of the Br, right? One of the Br, it's bonded to the carbon atom as a Br plus, and another bromine takes a bond pair of electron and it goes as a Br minus. So this happens, this bromonium ion forms during the intermediate stage. Once the bromonium ion forms, then the Br minus, second Br minus, it attacks the carbon from the back side of the bromonium ion, where the bromine Br plus is there, bromonium ion is there, and the opposite direction, right? On the opposite direction, the Br minus comes and attacks. So when it attacks from the opposite direction, this Br plus goes on one direction, and in the opposite direction the Br minus adds on the carbon. So finally you will see the trans product as you are seeing here, right? So this is a common mechanism for electrophilic addition. That is the reason in all the addition reaction always gives a trans product. So the main reason is the formation of the intermediate three-membered cyclic intermediate state, which is a bromonium ion here, and if we use some other reagent, that may form different kind of cation here, right? Cyclic intermediate. Okay. And the electrophilic addition of halogen halides. So we have seen a symmetric molecule, that is the bromine, which has both Br or if we have some other halogen, means chlorine, means it will be a ClCl. If we when we add a unsymmetrical molecule, for example HBr, hydrogen halides, or HBr or HCl. So if we add, there are two things, right? H plus and Br minus. Whereas in this case, both bromines are positive and negative. So there is no matter. There is not a matter, right, where the Br minus is adding, where the bromine plus is adding. So wherever the carbon is adds, it will give the symmetrical product, but here it gives an unsymmetrical product. For example, if the H plus adds on the second carbon, you get one bromo propene, one bromo propane, right? If the hydrogen adds on the terminal carbon, that is the C1, then we get the product 2-bromopropane. So there is a possibility of two products, right? Mixture of products can be possible. So which product will be the major product, that we need to see. So for that, there is a scientist called Markovnikov. So he made an empirical rule, that is the Markovnikov rule. So what he said that the negative charge of the hydrogen halide, right? So that negative charge species always goes and attacks on the less hydrogen having the carbon atom across the double bond. So that means the 2-bromopropane, which has one hydrogen atom, the propane, that means the C2 carbon has one hydrogen atom, and the C1 carbon has two hydrogen atom. So the Br minus will always go and attack on the less hydrogen containing carbon, that is the C2 carbon. So 2-bromopropane is the major product according to the Markovnikov rule. So why he said that that will be the major product? The reason is, so when, again the same principle, when this H plus and Br minus come closer to the electron rich alkene center, there is a partial negative partial polarization of the bond, right? So the H plus can go and add either, first the H plus can go and add either the C1 or C2 carbon, right? So if the H plus adds on the C1 carbon, let's see here, right? If the H plus adds on the C1 carbon, there will be a CH2. There is a CH3 and CH plus. As the H plus adds here, the bond pair of electrons will be coming to CH2, and there will be a positive charge on the CH. So you get a secondary carbocation here, right? If the H plus adds on the C2 carbon, then there will be a positive charge on the C1 carbon. That means you get a primary carbocation here, right? So now we have to consider about the carbocation stability. So according to the carbocation stability, the secondary carbocation is more stable compared to the primary carbocation, right? So by seeing that, the secondary carbocation will form as a major intermediate, and once that forms, then the Br minus go and attacks the secondary carbocation. So we get here C2 substituted, that is the halogen atom is substituted on the C2 carbon. So that will become the major product, and that is the only one product will be observed according to the Markovnikov rule. Okay. So now in this case you take a HBr. Now in the C2 carbon there is no hydrogen, that means that is the least number of hydrogen. Even it is no hydrogen or one hydrogen, we can say, we compare with the next carbon and say that is the least number. So now the hydrogen goes and attacks on the first carbon to generate the tertiary carbocation, and the Br minus will go add on the second carbon, that is the tertiary carbon. So the major product will be 2-bromo-2-methylpropane. Okay. So that is the thing we are seeing here as a simple structure, right? So here we have written as a CH3, and here we have given as a simple structure. So if you take a phenyl instead of a methyl, so what it will give? Again, the phenyl will stabilize the carbocation. If the phenyl, the carbon forms near to the benzene ring, that is the phenyl ring, that will be stabilized more by the resonance structure, right? So that carbocation will be more stable. So the bromine will attack on the carbon where near the phenyl group is there, right? So that is the most major product. And in this case we have a electron withdrawing group, that is the nitrile group, C triple bond N group here, and which is attached on the alkene group, right? So when we add HBr on this, now it will occur on the opposite trend, opposite to the Markovnikov rule. The reason is, if according to the Markovnikov rule it happens, then the positive charge will create on the less hydrogen bearing carbon atom, that means the C2 carbon atom, right? But near to the If that forms near to the carbocation, there is a strong electron withdrawing group, that is the C triple bond N, right? So this electron withdrawing group destabilizes the carbocation, right? So this destabilization will not entertain the product formation. So the primary carbocation formation, which is relatively apart from this electron withdrawing group, that will be the relatively stable carbocation among this category. Compared to the secondary carbocation, the primary carbocation is the relatively stable. So this bromine minus will attack the primary carbocation, so we will get the bromine attached to the carbon where we have a more number of hydrogen atom. That is the anti-Markovnikov product. Okay. And in this case, for example, if we are having 2-pentene, if we have a 5 carbon atom and the double bond starts with the second carbon atom, here in this case we have the double bond which has the hydrogen atom both 1-1, right? There is in this carbon we have one hydrogen atom, and in this carbon we have one hydrogen atom. So here there is no more number or less number of hydrogen atom. We should say the hydrogen numbers is same on the double bonds, right? So here we can get the mixture of product, because there is a 50-50 chance where the hydrogen can go and attack either of the carbon. Wherever the hydrogen can go and attack, we always get the secondary carbocation, right? So we always get the mixture of product in this case, that is 2-bromopentane 50% and 3-bromopentane 50%. We will get in a 50-50 ratio, right? And if we add a HBr across the ethylene, that is the acetylene, we get a tricoupled product, right? So the first HBr will occur without any carbocation stability or without any condition, without any Markovnikov rule or something, because here one hydrogen, here one hydrogen, so the hydrogen can go and attack any kind of carbon, so we get the same product, right? And in the second HBr addition, there is a formation, we need to see the carbocation stability, right? So for example, if the first product formed, then the second H plus where it will go and attack. If the second HN go and attack on the bromine atom where it presents, right, we get here we get the primary carbocation, right? But if the hydrogen atom goes and attack on the carbon atom where the H is there already, right, then we get a secondary carbocation here, right? So the secondary carbocation is more stable, then the bromine will add on this secondary carbocation. So we will get the product where the two bromines are attached on the same carbon. So we get 1,1 dibromoethane, that is the as a major product. And this follows the Markovnikov rule. Addition of water. Okay, so now we comes to the water addition. That means previously we have seen hydrogen halide, now here we are going to see a water, that means HOH. So instead of bromine Br minus, here we are having OH minus, right? So this happens always in the presence of the H plus, because we need a protonating agent to initiate the protonation through acid catalysis, right? Again, this also follows the same Markovnikov rule. So the Br minus, the OH minus will go and attack on the carbon where it has the less number of hydrogens, right? So we get the secondary, that is the secondary alcohol, that is the isopropyl alcohol as the major compound. Okay, so it follows the Markovnikov rule. Okay, so let's say in this case, okay, so in this case what happens when there is a formation of the secondary carbocation according to the Markovnikov rule, but there is an rearrangement is possible. So because of the rearrangement, we may have a tertiary carbocation which is more stable than the secondary carbocation, right? So once the tertiary carbocation is formed, then the high OH minus will go and attack on the tertiary carbocation. So it always relative stability where there is a possibility of formation of tertiary carbocation, then definitely the tertiary carbocation will form over primary and secondary carbocations, right? Then the product formation will be substituted product of the tertiary carbocation. So this also follows the Markovnikov rule, but after the Markovnikov rule, it makes a rearrangement reaction, right? So that this kind of rearrangement we already have seen in the previous model, that is the kind of Wagner-Mervin rearrangement, right? And the carbocation reactions we have seen in the previous model. Okay, and addition of water can also be possible using mercuration, demercuration. Okay, oxymercuration we would say, that is called a mercuration and then demercuration. For that we use the reagent called mercuric acetate. Okay, so we take a double bond and add mercuric acetate in presence, water in presence of mercuric acetate. So first here the mercuric acetate will bond with the uh, where the more hydrogen number is there. This addition also is possible, occurs according to the Markovnikov rule. Okay, so here hydroxy mercury compound forms as intermediate, and then where the carbocation forms means the secondary carbocation forms where the OH minus go on the attack, right? So after this mercury compound formation, we add the sodium borohydride. That sodium borohydride will reduce this mercuric hydroxy mercury compound and produces the alcohol, that is 2-butanol. Okay. So this is a reagent we use for the alcohol formation for the addition reaction. And another important reaction is the hydroboration, right? So hydroboration is one of the very important reaction where we can add alcohol. The important thing is that this is the only hydrogen reaction where we can get alcohol formation with anti-Markovnikov product. Okay, so that we see. So here is the borane, diborane, right? Boron compound. So we take a diborane or any kind of substituted borons, okay, tri-substituted borons. Since the boron has a more electron deficient center, it always attacked by the electron rich center where more electron density is there among the two carbon atoms, right? So when we see here, this boron will be always added to the terminal of the carbocation. So where the terminal is there, it will be attacked from the carbon by the to the boron atom, right? So as you see, the terminal carbon attacked the boron, and then the positive charge, the carbocation formed on this second carbon atom. Okay, so next the hydride ion transfer, the hydride ion shift from the diborane that comes and attacks the carbocation formation. So as you see here, the alkene attacks the boron center, and the boron then forms a secondary carbocation. The hydride ion, H minus comes and attacks the carbocation to produce the compound. So once this diboron is formed, since the boron has 3 valency, so this diboron formation will not stop only at this one substitution. It will always go 3 substitution. Okay, like this. It will not stop at 1. It will go like a 3 substitution. So in one boron atom, 3 alkane atom will attack, and then it makes a 3 substitution. Right. Once this 3 tri-substituted boron formed, then we use sodium peroxide and hydrogen peroxide and sodium hydroxide to oxidize this boron carbon bond. So once we do this oxidation using this reagent, we get a alcohol as a functional group here, right? So we see the example here. So the electron rich center would be this carbon, that is after the addition of the boron, the formation of the carbocation will be more stable on this tertiary carbon. So the hydride ion comes and attacks on the tertiary carbon, right? And then after the oxidation through hydrogen peroxide, sodium hydroxide, or using sodium carbonate in hydrogen peroxide. You need a base, any base, and then hydrogen peroxide, that is must. Okay, so that is the oxidation reaction which converts the dibor into alcohol. Okay. So here is an example for oxymercuration reaction. So oxymercuration reaction, you get the product of like a Markovnikov product, right? And in the hydroboration, you get the anti-Markovnikov product. Okay. And then stereochemical aspect of halogen addition to alkene. So initially we have seen the addition reaction always occurs on the always gives the trans product, right? So here we can see in a stereochemical manner, right? So trans product means it called as a E substituted product. Okay, so here you see we take a compound, that is the stereospecific or stereoselective reactions. There comes another term, stereospecific and stereoselective reactions. So stereospecific means, for example, if you take a starting material as here cis, okay, and it has to give a trans product, means it has to give 100% trans product only. There is no mixture of cis or trans product. So once one starting material or one configuration gives only one selected configured product, that means stereospecific. Stereoselective means there may be a chances, right? Either or, it can form cis or it can form a trans product. So that is stereoselective, right? So these elimination reactions always stereospecific reactions, because addition of any atom or molecules on the double bond always gives a trans product. So that is a stereospecific reaction here. So you take a cis alkene here and you add a double bond, so you add a bromine here, bromine molecule. So you get a first formation of the bromonium ion, and then next the bromide ion, it always attacks from the back side of this bromonium ion and it gives the trans product, right? So if you tilt that stereochemically, you will see that trans product. Okay, so this cis alkene gives the trans product. And similarly you take a trans alkene and then again add the addition, bromine addition will be always on the trans. Okay, always you get, but when you tilt that, you will have a different product, different product in the sense you will have the trans product, trans addition only. Okay, always there will be a trans product. You see here the cis gives a trans alkene and the trans gives a trans bromine. So when you tilt it, that you will have a cis orientation, and so that you will observe that both the bromines are in the cis direction. But if you tilt this to a methyl group as a trans position, as like in the starting material, you will see the both bromine will be on the trans position, that is the trans product. Then bromonium ion as intermediate in the stereoselective reactions, right? So there are stereoselective reactions, as I said. So in this case, you take a steel beam and add bromine, okay, bromonium ion, bromine here. So there is a 50-50 chance of making stereoselective product. Okay, so if you add another nucleophile, for example in this case you add water, OH will be the nucleophile. So once the bromonium ion forms, then OH will come and attack. So when this bromonium ion forms, it is a symmetrical bromonium ion, right? So the OH can go and attack any kind of carbon to make a stable carbocation radical. So the OH or water molecule has 50-50 possibility to attack any kind of carbon to give the same product, as you can see there. Okay, and in addition, so here is the NBS bromination followed by nucleophile, that is the alcohol addition. So here you can see the addition will be a trans product. Okay, and it is another example, and here Even though it's a trans product, there is a selectivity. Since it is a symmetrical double bond, there is no much selectivity, but here there is some selectivity because the carbocation forms after the bromonium ion. The carbocation forms on this tertiary carbon where the methyl group is substituted. That will be the most stable carbocation. So the alcohol will go and attack on this tertiary carbon rather than the secondary, rather than this carbon, that is the secondary carbon. Okay, so you get this product as the major product, but the addition is the trans addition. You see, the bromine and the alcohol you are adding, the bromine and alcohol both are in the trans positions. Addition to conjugated diene. Okay, so far we have seen addition to the only one double bond or only one triple bond. So now we are going to see more than one double bond, that is the more than one double bond, that is the two double bond or three double bond. Okay, so 1,4 pentadiene. So we have a two double bond here, so there is a possibility of having 4,5 dibromopentane, right? Since the conjugation is break here, we should have a selective product either from 1,2 substitution only. We can have the product here. Okay, but if it has a conjugation, it is in the conjugation, means for example 1,3-butadiene, there is a possibility of two product formation. One is 1,2 addition product and another one is 1,4 addition product. So how the 1,4 addition product forms? Because of the resonance structure, right? And also there is a formation of the stable carbocation, that is the allylic carbocation, that we will see in the next slide. You see here, so first the electrophilic attack, that is the H plus, it makes primary carbocation. It has to go and attack any carbon, right? It makes a okay. So the H plus attacks on the first. Let's see. If the hydrogen is attacked on the C2 carbon, we will have a primary carbocation. Whereas if the hydrogen is attacked on the C1 carbon, we will have a allylic carbocation. So the allylic carbocation will be stabilized by the resonance structure. Whereas in the primary carbocation, there is no stabilization effect, right? So it cannot be stabilized. So the allyl carbocation is most stable, right? So the bromine Br minus can attack on the C2 carbon, or through resonance structure the double bond can come here and the positive charge will be on this terminal C4 carbon atom, right? Like this. So the bromine attack bromide ion can attack here. So 1,2 or 1,4 addition product can be possible here. Both products are possible products. And similarly, if you add HCl, the same way you get 1,4 addition product or 1,2 addition product, both you will get. Oxidation of alkenes to form epoxides. So now, so far we have seen only the hydrohalogenation or hydration. Now we are going to see an oxidation. So oxidation, if you oxidize the double bond, it's an epoxide oxidation, right? There are many oxidations. If you oxidize a double bond, it can give dihydroxy compound, or it may even give aldehyde, or it may give ketone, right? So depending on the oxidizing conditions, it can be the product. Here we are going to make a epoxide by using some famous reagent called metachloroperoxybenzoic acid. We say MCPBA. Okay, MCPBA, metachloroperoxybenzoic acid. This is very important reagent for generating epoxy from the double bond. Okay, so the mechanism you can see here. Since this black color oxygen is more electron deficient in nature compared to other oxygen, so the alkene attacks first the carbon, first the oxygen, electron deficient oxygen, then this you can see the arrow, then this OO bond breaks, and then the lone bond electrons comes here, and this C double bond O bond breaks, pi bond breaks, and then it gives a new bonding, OH bonding to the hydrogen atom, right? So you can see here in the transition state how the bond formation and bond breaking occurs to produce the epoxide ion, right? So you take a steel bean, trans steel bean, and add a metachloroperoxybenzoic acid, we get a trans steel bean product. And you take a cis steel bean, we get a cis steel bean product. So this also, if you take a trans product, cis product, that means this is a stereospecific product, stereospecific reactions. Okay. And this formation of the epoxide depends on the electron density of the alkene. For example, the reaction rate, if you have only one double bond, the reaction will go as like kind of a relative rate. If you have only alkene, let's consider that is a reaction rate is 1. But if you have one extra methyl substitution, the reaction rate increases. If you have 2 methyl substitution, the rate increases like 500 times, right? Now if you have 3 and 4 substitution, the reaction rate goes very fast. This is because of the electron rich, increase in the electron richness of the double bond by attaching the plus I inductive effect group like methyl groups. So when the electron density increases, there is a lot of electron available to easily attract this electron deficient oxygen, right? So that the epoxide formation will be very fast. Okay, now there comes an selectivity now. So far we have seen only one bond where the epoxide can be formed, right? Now if we have a two different kind of bonds, for example, this double bond has tetra substitution and this double bond has di substitution. So on which bond the epoxide formation will occur first? It relates to the electron density. As the tetra substituted bond, both are substituted the alkyl groups. That means plus I effect, plus I inductive effect groups are there. So that means compared to this disubstituted double bond, this tetrasubstituted double bond is more electron richer. There only the first epoxide formation will occur, right? So you get the selectively this product. Okay. And here is another example, the epoxide ring opening. Okay, so you take an unsymmetrical double bond and epoxide. Okay, so you get a epoxide here, and then now you add an nucleophile. Okay, so now by adding the nucleophile, the epoxide ring opening is depending on the conditions. For example, you have two nucleophiles. The nucleophile is same. The nucleophile is methoxy, but you have a different kind of conditions. One is methanol in acidic condition, that is nucleophile in acid condition, and nucleophile in base condition, that is sodium methoxide, which is in the base form, right? So now let's say when nucleophile is in the base condition, that is strong nucleophile we would say, and nucleophile in acidic condition, methanol in HCl, that is kind of a weak nucleophile we would say. Okay, so when there is a weak nucleophile, it always depends on the most formation of the most stable carbocation. Where the most stable carbocation formation is possible, this nucleophile will attack that carbon. Whereas when you have the strong nucleophile, where the least hindered site is available to attack, there it will go and attack. For example, this carbon has two substitution, whereas this carbon has only one substitution in the epoxide, right? So the base nucleophile will always attack the least hindered side. That means where one substitution is there, that is the least hindered side. That side the methoxide ion will go and attack, right? And the epoxide ring opens and you get the OH for this epoxide ring opening. And when you have weak nucleophile, that is methanol in HCl, here the formation of the carbocation will be more stable in tertiary carbocation compared to the secondary carbocation. So the methanol, that is the methoxy group, always attacks on this tertiary carbon site, and then ring opening of the epoxide, and it gives the OH minus, right? So it depends on the relativity. So the mechanism you can see here, how the epoxide ring opening is happen, right? At acid condition, first the acid protonates the epoxide oxygen, and it is easy to open the epoxide ring. After the protonation, the methanol, weak nucleophile, comes and attacks the site, attack the carbon where the carbocation, that is the tertiary carbocation, can form, right? It attacks that center, and then the epoxide ring opens. After that attack, the ring opens completely, and then the hydrogen from the methanol that comes and adds on the water, or it leaves as a acid catalyst. H plus leaves as a acid catalyst, right? So this is a epoxide reaction. And then metal catalyst for alkene reduction. So we could use some of the metal catalyst, that is reduction of the double bond, right? We would say that is addition of hydrogen molecules. So there are famous catalysts called a Wilkinson catalyst. So the Wilkinson catalyst, it's made up of a rhodium metal, where you have a 3 triphenylphosphine and 1 chlorine, and rhodium has a +1 oxidation state. Okay, so that is the rhodium catalyst you see here, which is in the square planar structure. Okay, and when you have a metal catalyst or complex, it always goes kind of a oxidative addition and reductive elimination reactions. Okay, so that and all you will be seeing in the next upcoming classes, or you will study in the inorganic classes. Okay, so when you have a alkene and you have a catalyst, rhodium catalyst, so the and also you have to send a hydrogen gas along with this rhodium catalyst. So first the hydrogen gas added on the Wilkinson catalyst. As you see here, the addition of a hydrogen removes one of the PPH3 triphenylphosphine, and the hydrogen is added here, hydrogen molecule. After addition of the hydrogen molecule, the alkene, which attacked by rhodium, so this is called a kind of a oxidative addition reaction, right? Oxidative addition. So as the oxidative addition happens, one of the hydrogen is added to the double bond, and the terminal of the double bond, the terminal carbon of the double bond always attaches to the rhodium metal, right? So once this is formed, then reductive elimination is the next step. So that means the hydrogen which is attached on the rhodium will always come and attach with the terminal carbon of the alkene, and then after addition of the hydrogen, this completely come out, so we get a reduced product. Okay, so this is the mechanism of the Wilkinson catalyst. And another important catalyst is Lindlar's catalyst. The Lindlar catalyst is the combination of palladium calcium carbonate or palladium acetate. Okay, so this is the combination of Lindlar catalyst. So the Lindlar catalyst reduces the alkyne, okay, C triple bond C, and it produces alkene, or it produces alkane, right? So you need again a hydrogen gas you have to send. So this Lindlar catalyst always gives the cis product. The reason is that this alkyne has to bind on the the hydrogen molecules, hydrogen gases will bind on the metal surfaces. So when it is binded on the metal surface, the addition possibility is that it can attack the unsaturated compound or unsaturated double bond through one side only, right? That means the cis product only is the possible. And dissolving metal reductions, this is another important reaction which is called a Birge reduction. In Birge reduction we use liquid ammonia and then a metal called sodium or lithium, any metal we use. So this dissolved metal hydride Birge reduction also reduces the alkyne, reduces the C triple bond C to C double bond C. Okay, so this reaction is always a again stereospecific reaction. This dissolving metal reductions always gives a trans product. Okay, so you can see the trans alkene as a product here. So you can see the mechanism of Birge reduction. So Birge reduction, it uses the metal, right? Dissolving metal reductions, right? So the metal always gives electrons very easily. So there will be always an electron, kind of a one electron, it always available from the metal. So that electron will first go and attack on the acetylene center, and it forms kind of a radical anion, right? And then this radical anion will the anion will take one proton from the ammonia, and the hydrogen is added and it gives a ammonium ion, and there is another electron which is coming from the metal, right? And that metal, the two electrons combines each other and it produces a carbon ion. Carbon ion produced. That carbon ion abstracts the proton from ammonia and it generates the alkene, that is the transalkene. So here the formation of the carbon ion always makes the anti periplanar state. So it prefers the anti because the electron density, it always try to away from the other steric factors. So it always stay in an anti periplanar state. It makes a anti-parallel state. That's why it gives the anti-product. Okay. And bridge reduction of arenes. So it also not only reduces the alkyne, it also reduces the aromatic rings. For example, you can reduce the benzene using lithium liquid ammonia to get the reduced benzene. So how this reduction happens in the aromatic compounds? So similar like the same mechanism. First, the metal gives an electron, and that electron goes on any carbon of the benzene of the pi orbital of the carbon, right? And then it generates through the resonance structure. It generates the anion, and that anion takes a proton from the solvent. Here we use the solvent as ethanol. So first it takes a proton, and then that carbon reduced to CH2. There the aromatization breaks, and then second it remains one electron, and another metal gives another electron. So combined it makes an anion. That anion is resonance stabilized like this structure. So once this resonance stabilized structure is formed, the possible so there are two resonance structures possible. So to reduce the steric hindrance, the para position anion which lies on the para position will be the most stable as like the trans product. So the protonation occurs on the para position. So the aromatic rings reduces at the para positions. And here we have different kind of substituent. For example, if we have electron withdrawing group on the benzene ring, how the benzene reduction will occur, or if we have the electron donating group on the benzene ring, how the reduction can happen, right? So it depends on the relative stability of the uh, it depends on the relative stability, right? So first we take the electron withdrawing group. For example, take a sodium that gives an electron, right? So it reduces first one position. This we will see in the next slide how the mechanism occurs, right? See here. So the sodium gives an electron. That electron gives will be taken and then it produces the anion, right? So that will be that anion will take a one proton, right? And then the second electron which is given to the benzene ring, it makes a carbon ion. Now the formation of the carbon ion will be stabilized by this electron withdrawing group. So that where the COOH group, electron withdrawing group attached, that carbon will be stabilized, stabilize the carbon ion, right? So there the proton will be the carbon ion abstracts the proton, and then the reduction happens on that same carbon where the electron withdrawing group presents, right? Whereas in electron donating group, the first um, anion generates just meta or para position to the electron donating group. Since the anion is more destabilized by the electron donating group, so this that will happen, or the anion generation happens meta or ortho position to the electron donating group. And then the second electron which is coming from the metal, that forms an anion that is in the meta position, because the same reason, the electron donating group destabilizes the destabilizes the anion if it presents para position or ortho position to that. So the meta position will be relatively stable. So the second reduction, the addition of second proton will always occur at the meta position, right? So here you can see a summary. Electron withdrawing groups promotes ipso para bridge reduction. Ipso means where the functional group is there, the same carbon, ipso para bridge reduction, and electron donating groups promote ortho meta bridge reduction. And then concerted addition reaction. So this is the famous reaction called the Diels-Alder reaction, where the diene and then dienophile, right? Dienophile means a simple alkane, right? And then diene, which has the cis-in conformation. So both will occur, and immediately it forms, both will join and immediately forms a compound, right? So there is no intermediate, in this one. So it's kind of a electrocyclic reaction or kind of a pericyclic reaction, we would say. So it's kind of a concerted reaction. So just an electron movement and it forms the bond. What is called a Diels-Alder reaction. That is the reaction between diene and dienophile. So it's kind of a addition reaction. That means you are adding a group, that is the cyclic group among the double bond or the double bond. So here are different kind of asymmetric dienes and then dienophiles. So how the reaction can happen, how the products formation can happen, that you can see here. Mostly that is a homo-LUMO connection, right? So the detailed discussion and all you will see it in the master's degree level. So right now you can just see what kind of product can give a this sort of product. And then conjugate addition. So conjugate addition in the sense a double bond which will be conjugated with the another double bond or another carbonyl group. Here we see the carbonyl group, that we can say this compound as a alpha beta unsaturated carbonyl group, because the double bond presents in the alpha and beta position to the carbonyl group. So now when we do addition to this double bond, there will be a addition at alpha and beta position to the carbonyl compound. So you can see here the amine group dimethylamine, which is added on the beta position to the double bond, that is the alpha beta unsaturated carbonyl compound. So through the resonance structure, the anion is stabilized, and then while regenerating the carbonyl group from the anion, inert anion, it abstracts the proton and the formation of the reduced product. Okay, as you can see here. So that's it. That's all about the addition reaction here. Hope you understand this lecture. Thank you.